pleased to have the opportunity to do this, partly because it forced me to go and figure out what's actually going on in some of the aspects of synchrotron radiation. I was asked to do synchrotron radiation past, present, and future, and that didn't sound very interesting to me, because the impact of synchrotron radiation on structural biology can be summarized rather quickly. We've already learned there are 100,000 depositions in the PDB now. 10% of them appeared in last year. This is 50 per working day. Think about it, 50 new structures per working day, and 80% of those come from data measured at a synchrotron. At the same time, we've had multiple Nobel Prizes in the last several years that depended upon synchrotron radiation to have accomplished what those investigators did. For some of the other parts of structural biology, small angle scattering is in a, shall we say, a renaissance. In the mid-90s, Dmitry Svergin, working at a synchrotron at DAISY, developed software that was able to use the really high-quality synchrotron scattering patterns that they were able to observe. I wrote software firstly to just calculate the Sachs curve using PDB, and you can see that the pace of production of publications from that are high, but then really also important was this software that will give you some idea of what the shape might be that would match the curve. Here we have just other measures of the way that the increase in Sachs publications is increasing is increased by the number of synchrotrons that are appearing. So one might ask, how do they do that? I mean, we know that the advances in biochemistry and crystal growth are critical. Alex made that really clear to us. And so what is it that makes synchrotrons so useful? Well, the answer is that under the hood, there are several technologies, all of which have had, I think, Halliwell's word was colossal improvements in their quality. And we're going to review these technologies one at a time. You can see that we'll look at the sources. Well, how are they changing? We need optics to control them. We have to hold the crystals. We have to handle these crystals. The detectors are a very important part, and software ties it all together. So let's think about the sources. I recommend to you the chapter by Michael Hart in an old version of Methods of Enzymology, wherein he explains a number of things about how synchrotrons work. He gives this slightly misleading drawing. The point is that electrons or positrons are emitted, and they tend to travel in a straight line unless a magnet bends their path. And so the booster synchrotron is shown as a polygon. This is actually a polygon with straight sections determining separating the magnets, and radiation is emitted at several places, and we'll talk about these arrows now. So what is the source of synchrotron radiation? Well, you've today had at least two different explanations of it. I'm going to give you the cocktail party explanation. And you need to think of the electrons that are traveling essentially at the speed of light, and as these electrons turn the corner, if you're watching up the tube as these electrons turn the corner, what you see is this little electric field going one way and then the other. There's an induced electric vector as the electron becomes visible to you and then goes away again. And it's like flicking a string. You flick a string, and that is the alternating electric field of the photon going away from you. The harder the tighter you bend it, the quicker you flick it, the faster are the electrons, that is, the higher the energy, then the shorter is going to be the wavelength of the light. We talk about a characteristic wavelength. This is just one that's kind of near the center of the emission curve, going as the radius of curvature. In other words, The gentler the bend, that is, the longer the radius, the longer will be the wavelength, and then the energy of the electron is a very high power in the denominator. So if you want to make hard X-rays, increasing the energy of the field is one way to do it. The spectrum that we get is generally broad. This is an historic predicted spectrum for NSLS probably from about 1978. Nonetheless, we are predicted to get lots of radiation at the copper K alpha position and lots at the selenium edge from the standard bending magnet sources. We also show some charts from wiggler sources. What is a wiggler? Well, one can insert a multi-magnet device into the straight section of the synchrotron. So here I'll teach you a little jargon. Michael mentions insertion devices. The multi-magnet insertion device is what you use, and the wiggler would go roughly here in one of these straight sections in the synchrotron. The wiggler is essentially a row of alternating dipoles going first up and then down, and this will make the electrons wiggle in their trajectory as they pass. This particular configuration where the magnetic fields seem to go like this was invented by a man named Halbach in the Bay Area. The intensity from the wiggler goes linearly as the number of magnets. So you essentially get a new pulse of photons from each wiggle, and that gives you an indication of the increase in the intensity. On the other hand, there's another kind of insertion device called the Undulator. It's an array of magnets that's like a wiggler, but the magnets are weaker and the period is shorter. So as the electrons undulate, they don't undulate very far, and the electrons run right alongside them in a way that they interact with the photons that are being emitted. And each packet of photons then is going to interact with each successive magnet, and the intensity from the undulator is multiplied not by the number of magnets, but by the square of the number of magnets. And Michael Hart suggests that this is the way to think about this. It's as if it's diffraction from a one-dimensional lattice. So you have the n-squared term for the intensity of the emission. I was going to keep track of time. Here's a photograph of an undulator that's similar to the one that's now in NSLS X29. It's a mini-gap undulator. The gap between the magnets is about 3 millimeters. You can see that the total period of this one is about 12.5 millimeters, about half an inch. The magnets themselves are these gold-colored things, and their fields go in alternate directions, and then these poles bring the magnetic field up to the electron beam. A man named Oleg Chuar has some software that allows one to calculate the spectrum that you might expect from NSLS2 undulators, and this one right here, the 21 millimeter one with a gap of 5.5, is the undulator that we've chosen for the 2 MX beam lines that we're building for NSLS2. And so what you're seeing here is that the fundamental emission energy, which is right here at 1.5 keV, and then these are our harmonics. And if you count, it goes up to the 18th to 19th harmonic. Now imagine taking your guitar. You know how to strike a harmonic on a guitar, right? You just touch the middle of the string and you pluck it and you'll get the first octave, and then you go up here to a third of the way and you pluck it there and you'll get the next third. Imagine going all the way up to get the 18th harmonic. That could only be done with just a perfect string, a perfect pluck, perfect place for it to vibrate. So in order for this to work, the beam itself must be perfect, and this array of 280 magnets has to be precisely tuned to give this pattern of harmonics, and we expect to get that from these undulators. You've heard earlier today the idea of the emittance of the electrons. The emittance is defined as being the product of the size of the beam and its angular crossfire. So a combination of how big it is and how much the electrons are crossing is its emittance. And small is good. In other words, you need for the beam to end up being collimated. Hart explains that the synchrotron ring behaves like diffraction from another one-dimensional lattice, which is the entire lattice of dipole magnets all the way around the ring. And so you can see that if it's one-dimensional, then over this many magnets, there's going to be some power of n in it. And roughly the emittance becomes this. It's the square of the energy. So the high energy rings have trouble getting to low emittance. And something like the third power of the number of dipole magnets. Just as an example, the NSLS has 8 cells with 2 dipole magnets in each one, a total of 16 dipoles. Okay, NSLS2 across the street will run at about the same energy, and it's going to have 30 of these 2 magnet cells for a total of 60. And it will be a whole lot brighter than NSLS. You can see how this math should suggest that that's true. MaxLab in Sweden, if I read their website correctly, is going to have 20 cells with 7 magnets in each, or 140 dipole magnets. So the emittance that's going to be possible there is just phenomenal, amazing. And then ESRF is planning an upgrade, and they're going to have 32 cells with 7 magnets in each for an even larger number, but of course remember that ESRF has a much higher energy than these others. Well, anyway, you can see where we're going, right? That as time goes on, as improvements continue, synchrotron sources are going to be very, very bright. We have an ultimate undulator source available to us now, and this is the LCLS at Stanford. They took the old slack tunnel and created a LINAC that produced really short pulses. As short as 50 femtoseconds, I think they normally run at 50, as short as 7, I think they run it typically at 50. The undulator is 120 meters long. The one that I showed you for X21, for our beam lines is 1.5 meter long. So the X-ray pulses that come out are very intense and quite coherent. It's really an X-ray laser. Maybe you know this already, that the single pulses will completely destroy a protein-based specimen, but that happens after diffraction occurs. So anyway, this is a very interesting source. Whether it will supplant synchrotrons is an argument that is in progress at the moment, but it's clear that there are very, very interesting things that can be done with this. We have to control this sort of a beam, and I'm not going to finish on time. We monochromatize with a parallel beam using a perfect crystal, typically of silicon. One crystal monochromatizes, the other one sends the beam off horizontally, and it's Bragg's law that determines the wavelength. That's easy. We can focus X-rays by doing reflection at very low angles. It's the same physics as internal reflection in the prism, and the angles are really quite small, 1/4 of a degree roughly. We can bend the mirrors to get focusing. These days you'll hear of KB mirrors, a pair of mirrors, one to do vertical focusing, the next to do a horizontal focusing, which is appropriate since the beam starts out as being asymmetric, and so to do different focusing in the 2 directions is useful. We have in the past done had a single mirror shaped like a cylinder to do combined horizontal and vertical focusing. And this is very useful when the beam is highly convergent, as one would get from a dipole. And here's a picture of the mirror that used to be an X25. You can see it's cut to a cylinder, and then we bend it with this mechanism to make a toroid, roughly an ellipsoid of revolution. It gave quite decent focusing, but with aberrations because it wasn't a perfect surface. So one of the technological improvements that's just absolutely dramatic is the improvement of the quality of the surfaces. How does this work? We have that the slope error is increased from 5 to about 1 microradian until about 2005. After then, new technology was developed. The RMS roughness could get down to 1 angstrom. This is sort of the short-term deviation in the surface, which is not the same as the slope or the shape of the figure itself. So the errors in the shape is going to impact the quality of the focus. Different pieces of the mirror will point the beam in different directions unless the figure is perfect. The roughness doesn't actually damage the focus, it just scatters light, and so the beam is weaker than you might have hoped. Let's do a little thought experiment. Let's say that I want to take this NSLS2 beam that's 4 microns high. The sigma is 4 microns, the full width half max is about 10 microns. And I want to set up a mirror with 10 to 1 Dmag that's going to give me a beam that would then be 1 micron high. What will happen with the various slope errors? Well, here I'm plotting sigma as a function of RMS slope errors. And indeed, if I have no RMS slope error, the sigma height of the beam will be the 4 microns that I start with. If I make it bigger and bigger, it takes off pretty fast. You can see that if we had this slope error of 0.2 microradians, 0.1 or 2 microradians, that would be pretty good. We would be close to the 10 to 1 that we wanted. On the other hand, if it got as high as 1 1/4, we'd be right back where we started. The image that we would get would be no better than the source that we started with. Now, how big is a tenth of a microradian? Right, a micro is 10 to the minus 6, so this is 10 to the minus 7 radians. Let's imagine I'm in New York and Eddie's still back here in Albuquerque. Right? And in New York, this is about 3,000 kilometers away, which is, of course, 3 times 10 to the 6 meters. I multiply that by the 10th microradian, and I get 0.3 meters, or 30 centimeters. So it would be as if here in New York, I could shine a flashlight at Eddie's foot, and then raise it by a tenth of a microradian, and it would come about up to his knee. Imagine what they have to do to make these mirrors that smooth. Well, some clever guys in Japan have figured out how to do that. They squirt a slurry of 2 micron quartz spheres in moderately high concentration on features. They have to be able to measure the surface of the mirror to find the high spots, and then they come along with this elastic emission machining to do the job. And they can get down to roughly 1 micron or 1 angstrom height of whatever it is that they want. So anyway, these nozzles are, the diameters are on the order from a millimeter or so, or they can make converging ones that would be less than half a meter. And they flow at rates of about half a meter a second, I think, something like that. So this is the way that these incredible mirrors are made. One might want to be able to adjust the curvature of the focus, and a company named Seiso in France have created a set of benders called bimorph benders, it's not a good name. They're piezoelectric bars that are glued to the sides of these solid mirrors, which could be glass or silicon crystal, and then electrodes are put on them. And piezo are materials that if you put a voltage across them, they will either shrink or expand, depending upon the size of the sign of the voltage. And they'll put maybe a dozen electrodes along the length of this. And then, of course, to make it curve upwards, to make an ellipse, they would shorten the top one and lengthen the bottom one. And indeed, they can make small corrections all along the length of the mirror sufficient to make the curve that they want, so that they can end up with a roughly 13 nanometer RMS height. So that means just as you follow your figure, the height is going to go up and down by about 13 angstroms, but the figure still ends up being better than 0.2 of a microrad. So this is the technology that we expect to use to get this near 0.1, 0.2 microrad figure error. And as we saw from the graph, that's what we need in order to get a 1 micron beam. Diffractometers. The Art Wanacott camera was invented back in the 70s. It was just X-ray film, but it was much more efficient than any other method that was available for measuring protein diffraction method. I mean, you need to remember actually that it was Art and Alan Wanacott who really invented the method that we use for essentially all protein data collection these days with monochromatic radiation. A modern commercial microdiffractometer, which wouldn't use film, is the MD2, invented in Grenoble by Tassos Perakis and Florent Cipriani in about 1999. It has sufficient precision reproducibility to handle crystals down to the range of about 5 microns. It's about this big. The one that we're using for similar applications at Brookhaven, we actually handle crystals down to about 20 microns, was one created by Chuck Strauss of Crystallographic, especially for X25. And I point out that the steel frame for this is quite stable because the device, again, is able to handle crystals that are several microns. The basis of this is having an 8-inch diameter air-bearing motor, servo motor, and the XYZ stage on it is really massive. The Crystallogic goniometer is equivalent, as I said, to the MD2, and we can handle several micron crystals with that. But those times are gone. We need to move on to a new generation of technology because our new NSLS beamline should produce a beam that's a micron wide and a half a micron high. You know, remember a yeast cell is about 5 microns on the side, yes, and this beam will be that small. It will produce 10 to the 13th X-ray photons per second continuously. The specific loading, you can do it, flux over millimeters squared, 10 to the 19th, 2 times 10 to the 19th photons per second per square millimeter. We expect the crystals to last about 60 milliseconds. So in order to handle this, we need new components. The next generation of the Aerotech air-bearing servo motor is fast. It's angular, very accurate in its angular setting, and it will give 20 nanometer positional stability. It will rotate about a point 20 nanometers in diameter. In order to do the XY orientation of the thing, there's a set of piezo stages by a Swiss company named Smarak that are fairly strong. They'll move fairly quickly, and they have a positional reproducibility of about 26 nanometers. Just amazing pieces of equipment that we'll put together to make the diffractometer that you'll need to handle these 1 micron beams. Handling crystals. We've had a revolution in this. In the before cryo days, here at X12C, you can see a crystal in a capillary with plasticine and beeswax and a drop of mother liquor inside the capillary. And at the synchrotron, this led to rather rapid damage. The crystals would last a while, but here Elspeth documented this browning of the lysozyme crystal measured at a second generation beamline. These days, of course, we use cryogenics, and here's an old diagram of the way it is done. In these days, the system is much simpler. The apparatus that we need are commodities. You can buy them off the shelf from Mightygen and Hampton and others to give you devices that are very easy to use and work just splendidly. We have automated systems. This is the one that we have had at X12B for some years, a pneumatic system that can pick crystals out of here, put them on the diffractometer. Typically, on our faster beamlines, we can handle a crystal every couple of minutes using this sort of system. And it completely changes the way one thinks about doing diffraction experiments. As you know, you simply can mount up as many as you want and be sure of being able to look at all of them during the period of your data collection at the synchrotron. We have a special purpose robot intended to handle crystallization trays that are designed to have a very thin window, a wide angle at the back, so that we can firstly test crystal diffraction with these, and then secondly, even to take a bit of rotation data within that range of rotation. More recently, in our group, Alex Suarez has discovered a method for handling crystals called acoustic droplet ejection. Here these very high, do we have the, no, we don't have the frequency. Anyway, these are megahertz frequency sound pulses that will create a droplet of liquid that will travel a few millimeters at very reproducible volumes, very reproducible production at a high speed. So we're able to mount crystals onto Mightygen grids, multiple crystals, take data from all of them, and get structures with just a little bit of data collected from each of very tiny crystals. Kristen Russler, Alan Orville, and others have created a conveyor belt system here. This is a Kapton conveyor belt that runs around. You'll see that the central axis of this Kapton is on the goniometer head base, so that when you mount it on the diffractometer, you'll be rotating around that point. Here you can see a little tiny upside-down sample holder, a column of water that connects the two, and then a hypersonic transducer here producing the pulses that will spit the crystal up there. They'll be translated into the cold stream and then rotated to take data collection. A very similar device to this, Chris and Alan and others have taken to the LCLS, and they can put pulses of crystal droplets at a pace roughly that of the 120 hertz LCLS with a pretty high hit rate. Talk to Alan, he will never tire of explaining this experiment to you. Detectors. The early days, of course, we solved crystal structures with X-ray film. Chris Bingham actually came to me this noon and said, "Remember being there? That was in the days when they had a dark room." Well, this was the device, the Arndt Winnicott camera inside Beamline X12C. The film seemed expensive at the time when that seemed important. It's pretty linear in a narrow range, really good spatial resolution. It's hard to find detectors that good. On the other hand, the dynamic range wasn't very small, and it just took forever to do it, just an extremely, extremely inconvenient way to collect data. And so we moved on as quickly as we can. We needed electronic detectors. I'm naming here the early workers in the field. Willie Arndt is really the one who got started, eventually had the first commercial detector. George Reynolds and Saul Glenner at Princeton, working on similar things. Joel Henricks invented the MAR system. Strauss, Westbrook, and Nadet at Arbonne, and then Walter Phillips and Marty Stanton, and then eventually Saul Glenner continued work with CD systems. Chris and Neil developed the first large array detectors, and more recently, the Detectors company, led by Christian Broneman, are making the first pixel array detectors. What's all of this about? I will summarize this for you. Here you see when Westbrook and Strauss brought their detector, and here it's actually on that same table that we used for the Arndt-Wanacott film camera. They are testing their system. What is the light chain? A phosphor turns X-rays into visible light. There's a fiber optic taper, an electronic electrostatic intensifier, a lens, and then a CCD. They got their images with that. Very soon after that, Walter Phillips and Ken Collada from Brandeis brought this system here. It's similar to light chain, a phosphor image intensifier, fiber optic taper, and a lens, and then another CCD at the end. And again, this was all testing the thing to try to figure out how to do it. Soon after that, Willie Arndt got NRF Nonius to build this first video detector. John Helliwell showed you a picture of the one that Miroslav Popes installed at Daresbury at about the same time. And this worked pretty well. Again, the light chain is about what you expect, a phosphor image intensifier taper. In this case, instead of a CCD, they used something that they knew they could get, and it worked really well, the X-ray tube. The good points, could be driven very sensitively. It was shutterless data collection. That seems a big deal these days, but we did that back before 1990, and really the first automatic data collection system. When this thing came in the door, we were the first to say, you've got to reduce all of your data right here. And so we were reducing data in real time as they were coming out of the detector. The dynamic range wasn't very big, and the detector itself was pretty small. An important advance that came along just after that was the idea of using imaging plates. There's this plate with a heavy iron bromide or metal bromide in it with europium doping. If you shine X-rays on them, all of them will be absorbed. They will push the europium into a state called an F state, which keeps in that state until you irradiate it with a long wavelength light, and then emits a short wavelength light, which can be scanned out. Joel Henricks' company, MAR, made several different varieties of these scanners, and we had a couple of different ones of these. It was not really fast like a CCD, but it was a whole lot easier than film. In fact, it was better than the video detector. We replaced the video detector with one of these. But these days, most X-ray detectors are based on advances reflected in the 2009 Nobel Prize. There are probably only 3 or 4 of us in the room that recognize the significance of that prize. It was fantastic that in one prize they acknowledged the fiber optics and the CCD imagers that combined to create these detectors that we have been using. So it was some combination of Ed Westbrook and Steve, or Ed Westbrook and Strauss and Marty Stanton and Walter Phillips and Saul Gunnar, who figured out that you could bond these things together. Walter Phillips, I think, or maybe Ed was the first to bond them together. And this is one that was turned into a detector that we used at X12C, and actually the early images from the 50S subunit were taken on this detector. The modern commercial versions are big, they're fast, and they're accurate, and this is really the basis for that exponential growth in structures that we see now. They're fantastic detectors. They are, however, being supplanted rapidly by what we call pixel array detectors. There are silicon detectors at the front end that absorb the X-rays and produce some electricity. These travel through bump bonds into amplifier counting systems below. That's a drawing that Ron Hamlin gave me. The detectors that are coming along are like this. There is a market for these pixel array detectors. Detectors has made quite a few of these PX6s. This is one version of the PX6, 6 million pixels, 6M. It can frame pretty quickly, and they have orders for several more. They have orders for more than one of these Eigner 16Ms, which have smaller and faster pixels that we expect to operate at about 200 frames per second. When you go to their stall, ADSC will explain to you the HF4M, which is a detector that's in production now and will appear on the floor of the NSLS before it dies. Software drives the whole thing. One of the neatest things that I did was to respond to Jim Flugrath's suggestion. He helped me get the FAST running at Brookhaven, and he had this code that was driven by command lines, and he says, you really ought to hire a programmer and make a GUI for this thing. So we hired John Skinner, and here is that very primitive GUI that Jim called Madness. It's called the program Madness, and this is, you can see the command line, which is driven by the GUI behind it, and that worked really well. Eventually, very quickly, this became a program that ran the entire beamline. You could do wavelength scans, you could realign the whole beamline, all from this same code. We were getting bored with the data reduction. This was by the time that we had the AMAR 300 detector in place, and Denso was so reliable at doing this that we decided we should be able to write a script to pick everything up and do it with one button. So when you wanted to do it, you would find a little pull-down window, one button, and then this one button would come up, and it would be named one button, and you push that button, and then this thing would start up and run the program, and here you can see summarized all of the things that seem useful from a run of Denso. We like to think that this was the father of HKL 2000, but you can argue with Vladek about that. Anyway, we have to figure out what we're going to have for the future. These beamlines are going to run incredibly fast. We're going to have a database to keep track of the experiment. The basis of this is going to be that for most operations, Python will be the basic language that we use. Some of you have heard of EPICS. It's a sort of industry-wide standard for controlling instruments in science. We will have a middleware. This thing is sort of the signal passer to everybody else. One can have GUIs from here. One can have access from websites offsite. We will have Control System Studio screens for the local staff to use. The central brains of it is down here, all controlled by Python macros. There are various libraries to control the different devices. The area detector itself will operate by itself and send data off to the disk. The robot itself will have new code, and then there will be a processing server sitting here watching what's going on in real time. And as soon as images start to appear, you'll do some preliminary analysis and give a report to the operator. Here's what this is going to look like. And then as it continues, it'll finish up and one can process the whole data set. And then, as you know, there's going to be a need for handling all of these systems where we have many, many small crystals, the data from which have to be combined. And there's software appearing for all of that. So anyway, this is what the software will be like. The conclusions are pretty obvious. Technology is marching. I mean, it is helping the biochemists to do what they want to do with their structure, and all of these are going to contribute to the future, which we believe you will enjoy.